Hello. Good morning, good afternoon, good evening, everyone. Welcome to a new webinar. Today we have a special guest and a very great presentation. So I will start without further ado because we want to explore every single second of this webinar today. So the topic is why insects do not attack healthy plants. And we're going to hear from Dr. Thomas Dykstra why of that. A quick breakthrough introduction will be 5 or less minutes. The presentation with Dr. Tom will be about 65 minutes, followed by a Q&A of 20 minutes. So we'll be together for around 90 minutes. And as I said, we have the honor and pleasure to have Dr. Tom Dykstra talking to us today. And Dr. Elaine is also in the house, giving us her amazing energy. Dr. Adam, you know him, and I will be your host today. So without further ado, Tom, you can start.
Okay, let's do a little share screen action. All righty. You all have the first screen up, correct? Give me a thumbs up,
do.
Carla. Fantastic.
Yes, we do.
All right. As Carla said, the title of my talk, Why Insects Do Not Attack Healthy Plants, is a presentation that I gave probably over a decade ago. And so it has now become like a must-see. It's now spread on the internet as well. And so this has now built into a really large area of inquiry for me, so much so that I actually have 4 presentations on this. I'm only going to be giving you the first one today, but know that this presentation that you're about to see has spurred so many questions that I've had to come up with 3 other alternate presentations in order to sift this, because this is a relatively new topic, or probably is a new topic for most of you. So let us see if I can begin, because I need to introduce myself since some of you probably don't know who I am. So where did it all begin? For me, it all began at Rutgers University. Never went to Rutgers University. And as a matter of fact, I never even set foot on Rutgers University, but it did all start there because that's where mom and dad met. So because mom and dad met there, that is my beginning. And the reason why it needs to be mentioned right now is because my dad at Rutgers University majored in ornamental horticulture. And after that, he minored in economic entomology. So the plant insect interaction was established at that very early stage, even before I was conceived, as you can see. So that's where it all began. Now, for me, it didn't end there in New Jersey, because my dad got a job in Rochester, New York. That's where I grew up. So if you ever wondered what it's like to grow up in New York, and I'm not talking about the city, definitely the upstate part, then you need to talk to me, and I'll give you the lowdown about what lake effect snow is all about. And so that's where I grew up. That's where I went to elementary school, junior high, high school, all of that was there. And that's my upbringing. So when I traveled to college, I did not go far away. So I attended Cornell University. It was only 2 hours away. It wasn't too bad, but it was still a lot of the similar type of stuff. So you can see that my beginnings were all in the Northeast. And that's so even though I moved to 3 different locations designated by the stars here, I haven't moved much during this time. So when I was at Cornell University, I had every intention of becoming an entomology major, and that's what I enrolled in. Never changed my mind, even to this date. Absolutely think insects are awesome. And of course, you're going to get a smattering of them today. So that's the good news about Cornell. There is some bad news about Cornell. And if you've never been there before, we do get a lot of snow, not as much as Rochester usually, but the temperatures are usually a little on the cool side. And so this waterfall, I passed by every single day from North Campus when I was headed to class. So this one is not quite frozen. It can't completely freeze over, but I just wanted you to get an idea of where I grew up in New Jersey. I dealt with lake effect snow. Here I am at Cornell. And so when you've got this this Ivy League university, you know, where you are supposedly imparted with a massive amount of information and knowledge. And I could feel that descending upon me as I'm attending this university. It was then that I realized that I hated the cold. And so because I hated the cold, I knew I needed to get out. And so that's what I learned. One of the many things that I learned at Cornell. Where did I go? Well, could have gone to Pennsylvania. That would have been south. Could have gone to Virginia. That would have been south too. But I kept going. Traveled all the way down to the University of Florida, was introduced to the color green, thought it was really cool. I'd never seen so much green before. I dealt with a lot of white, especially a lot of gray. And now we had the sun was out, which was very nice. I had green and I found, you know, a home. It was that home away from home, but eventually became my home. So I matriculated at the University of Florida. And for those of you who are not aware where it is, it's located in North Florida. So we're not down in Miami. We're not dealing with as much palm trees as you would expect. So in North Florida, we've got a similar climate to southern Georgia. We do get snow, but it doesn't stick. But occasionally it will fall. But generally, the temperatures are quite mild compared to what I grew up in. And that's where I stayed. So I got my master's degree there. And when you get a master's degree, you specialize even more. So I had the BS in entomology. Yes, it was a general entomology degree. I took 15 courses in entomology. However, for the MS, you start to get a little bit more specific. And this is where I moved into neurophysiology. And so that's kind of what the master's was about. I stayed for the PhD. This one is a little bit off the beaten path because I'm now involved in bioelectromagnetics, or how electromagnetic fields are affecting insects. And that was for the PhD. And both of those were at the University of Florida. So I have got three three degrees in entomology. When anyone who is looking at this for the first time sees these degrees, they usually come away with the assumption that, wow, this guy knows everything there is to know about bugs. I mean, everything in the world, and absolutely nothing about anything else. And so that assumption is something which I hope to dispense with right now, because yes, I do have that the 3 degrees in entomology, and it really gets worse than you think, because I actually took 23 entomology courses in my 3 degrees, not credits, but 23 entomology courses at 2 universities. I don't know of anybody else in the world. I'm sure there's some people out there who have 3 degrees and have taken 23 courses, but I am just filled to the brim with insects. But I've had a chance to branch out, and you're going to see a little bit of that branching out right now. So what did I do? After the University of Florida, I had a choice of going wherever I wanted to go. Well, where am I going to go after what the image that you just saw that I had at Cornell? So I just decided to stay. I started Dykstra Laboratories. That was in 1997. I've been here for a quarter of a century. This office that you see behind you is the same place that I've been in since 1997. I have turned it into a laboratory and have been working out of it for a long, long time now. So I'm still in Gainesville. I'm now raising a family here, and this is now what I call home. What have I done? Well, there are a lot of things I haven't done, and one of the things I haven't done is publish, because I'm not allowed to, but I can publish patents, and I have loads of research that I'm not allowed to publish, but I have that too. This just gives you a little bit of a smattering of some of the patents that I've received. The last one is my favorite. I've just been notified that it's been preliminarily approved, determining odorant reception in arthropods. This is a subject that I will not be spending any appreciable amount of time talking about today. I've just got a quick slide, but eventually we're looking to get this. I think it's the 8th or 9th patent, and hopefully I'll be in a little bit better shape at that point. But I am really trying hard. If you haven't noticed, giving you my background, throwing these patents at you, throwing the degrees, throwing the 23 courses for one reason, and this is to try to impress you. I need to impress you. It's very important that I try to impress you at the outset, because what I'm about to say is going to rock your world. It is going to be introducing concepts that you did not learn in college. And so I might as well start out right from the get-go about where I'm going to go. Here's a statement. Insects only feed upon food that is considered unfit, nutritionally poor, dead, or dying. If you've never heard this before and you're being exposed to it for the first time, some of you are beginning to doubt me. and I can understand why. I was never taught this at Cornell. I was never taught this at the University of Florida. I'm pretty sure they don't teach this at Rutgers, and I don't know where else they would be teaching something like this. This is something that I had to discover afterwards, and you're going to get a smattering in this first of 4 presentations of what I'm talking about. So when I say that they're only going after food that's unfit, nutritionally poor, dead, or dying, what exactly do I mean? So if I take 2 grasshoppers, for example, and then I give them a choice, and this choice is between what you and I might consider unhealthy food or healthy food, what's going to happen? Well, most of you, based upon maybe your education, would say, well, some of them would go to the unhealthy food, some of them would go to the healthy food. I really don't care because food is food, and I don't think insects really give a whip. So they're just going to distribute themselves and they're going to start eating whatever they can. So that's what most people would say. That is not what happens. Insects will always choose what you and I would consider to be unhealthy food. They do this all the time. They are actually here for a reason. They are designed to do something like this. And this is why I need to spend this presentation helping you to understand, maybe even convince those of you who are not on the same page. And I completely understand why some of you may not be on the same page, but I'm hoping that you will be on the same page when I am done. So if I'm going to try and convince you to the best of my abilities that insects are eating crap, where am I going to begin? I know. Let's start with crap. So here we have elephant dung beetles eating elephant dung. This is what they do. This is what they're designed to do. The reason why this happens is because they are specialized in order to eat this elephant dung. They are not competing with us. Many of us have this errant opinion that, well, in order to stop the insects from eating our food, we need to kill them. We simply need to spray and take them out. But they're not competing with us. I'm not competing with elephant dung beetles. They can go ahead and eat this to their heart's content. I'm not touching this. I've got other things that I prefer to eat, maybe such as pizza. But I'm not going to go after elephant dung. They are not competing with me in that. Unless you think that I'm taking an exception, you should know that there are about 7,000 species of dung beetles out there. So because of this, I'm not cherry picking any of this information. I've got 7,000 species of about 1 million species of insect, and 7,000 of them are going after some type of dung, whether it be elephant, could be giraffe, could be cow, could even be human, but they're going after some type of dung. This insect group, these scarab beetles, are not competing with human beings. Neither are these. Subterranean termites, they feed almost predominantly on dead wood. There's a few termites that can feed on dying wood. Those are some exceptions I'm not going to go into right now, but for the most part, termites are going after dead wood. And so that's the key here. They're not going after live plants. They are not going after live trees unless the tree is in trouble. And that would be Coptotermes, but that's another story altogether. And so because of this, we've got different situations here. And there's another situation where I would say termites aren't competing with us. They want wood, they can have it. I'm not going to compete with them. Love bugs are another one. Love bugs are here in the Southeast, very common in Florida and Louisiana. Very bright, showy insect, black and red. They're usually found in copula, which is why they get the name love bugs. And they go after, what do they go after? They go after decaying vegetation. They don't go after vegetation. They go after decaying vegetation. So because of this, this is another clue as to what these insects eat. And this group is really good at what they do. I mean, there's a lot of decaying vegetation that they eat, and their numbers can get to be very, very high. They're often attracted to highways due to various, I think it's aldehydes and some other chemicals that are given off from gasoline, and they will end up on your windshield in very, very large numbers. I was warned when I came down here never to turn on my windshield wipers when this happens, and I decided to forego it because things were getting really bad and did turn on my windshield wipers once. We'll never do that again. Clothes moths, they're in the same group. We're not competing with them. I don't want to eat my sweater. I don't want to eat my pants. The clothes moths, they have a job to do. They eat clothes. They're going after wool. Some of the natural fibers they go after. They don't go after the synthetic fibers, but the clothes moths are going after that. And I'm not competing with them. They can go ahead and do that as long as it's not in my wardrobe. I'm relatively okay with at least, we know, 3 species of clothes moths that are attacking clothes or rugs or something of that sort. The same thing here. These are the things I love to show right after lunch. And I know some of you just had lunch because I just heard about this right before I got online. So these domestic beetles are eating what type of meat? Decaying meat. The decaying meat that is found on a particular skull. And they will also consume the hair off the bones too. They also eat dead insects in my insect collection. But these insects are very well known and extremely efficient about cleaning off skulls that need to be displayed in a museum. So that's what they do. They are often used in museums in order to clean things for display. Again, they're not competing with me. They can go ahead and eat as much meat off this as they want, but there is no competition there. Same thing goes with these flies. Many of these flies, the California flies, the green bottle and blue bottle flies, will lay their eggs on carrion. For those of you who are not aware, carrion is a dead animal, and that's what they lay their eggs on. They're not laying their eggs for the most part on live animals. There are some flies that do, but they usually are going after dead tissue. And so, but I'm not going to talk about that right now, but these are going after carrion, like a deer on the side of the road. We got plenty of those down here. And so these are the maggots that go after, and they're very specialized at going after dead meat, carrion. Cockroaches, wow. Do I need to say more? I mean, cockroaches should not be competing with us. We look at the things that they eat. We know that they're found in large numbers, for example, behind a refrigerator, which is what the picture is showing right now. But all of them are eating pretty much gross gunk stuff that'll be on the floor, on the walls, and food that is going bad, and they will eat it and they will proliferate in it. Again, the cockroaches are not competing with us. Same thing goes with Drosophila melanogaster. Hope I didn't bring up any bad memories of genetics for those of you who went to college and took genetics. But the fruit fly is known for going after overripe fruits, vegetables, and other organic foods that are damaged, fermenting, or in an otherwise state of decay. That's what they go after. These flies are not going after healthy fruits. So if you go into the stores, I have many times, and you see fruit flies flying around the fruit, you can still pick up the fruit and you can still take it home. But out of, because I'm an entomologist and I'm a geek and I sometimes don't have tact, I will go through and I'll start picking through to find the usual dead one, the one that's in trouble. And there could easily be a dozen, 2 dozen, or 3 dozen of these flies around that overripe fruit. And that's what they're concentrating on, not the good stuff that I might want to bring home with me. So these guys, another situation too, the stored product insects. We even have entire courses in the Department of Entomology devoted to stored product insects. Well, they go after food that begins to die. What do I mean by that? Well, they don't eat food. They don't eat our crop plants. But they do eat our crop plants after we cut them, harvest them, and then put them in a storage grain bin, or if we put them into a silo, if we're putting them into a warehouse, then these stored products and insects will come in and they will start attacking the commodity. They do not attack it when it's out in the field, but they readily attack it once it's taken, for example, into a silo on a farmer's grain bin. So we've got the India meal moth, very well known. People see it in bird seed. People see it in dog food. We have the tribolium, red flower beetle, and we've got the sawtooth grain beetle down there. These are some of the big heavyweights, and they're all doing the same thing, going after food that is in the process of dying or may even be dead. So this brings up a question, which I'm sure some of you are thinking, well, I thought this had to do with plants, and you don't seem to be spending as much time about plants as maybe you should. But I now want to bring you to this position of taking a look at this picture of Kauai that I took while I was there. What do you see? You see vegetation. There's a lot of vegetation. There's a lot of green. Got a lot of trees, a lot of shrubs, a lot of grass. It's green. Hasn't been consumed. There are a lot of insects on Kauai. I've seen a lot of them. I've seen a lot of insects eating plants on Kauai, and yet they haven't decimated the island. Why haven't they decimated the island? They should have decimated the island by now. It doesn't take long to go after such a small island and completely remove all vegetative matter from it. But they haven't. As a matter of fact, most of the plants that we see in front of us and that I observed while I was there are not being eaten. Why? Has anyone ever thought about this? Have you ever thought about the fact that most of the plants on planet Earth are not being attacked? Sometimes they're attacked readily, sometimes they're not. And so if this is the first time you're hearing about it, I'm happy to be the first one to introduce you to this concept. So this then brings you to, okay, so they're not attacking all plants. I see where you're going with this. Now, where do you want to go next? I would say, well, how do you know what constitutes a healthy plant? Can you look at it? Can anybody look at this plant and tell me with 100% certainty? I'm not talking 99 or even 99.9%. Can anyone tell me with 100% certainty whether or not this is a healthy plant or not? I would contest that most of you, probably all of you, cannot tell me whether this is a healthy plant or not. You can't tell just by looking at it. So what is a healthy plant? Maybe we need to define this before we go on. So what constitutes a healthy plant? Some would say, well, it's tall, because obviously it's not going to grow unless it's healthy, and healthy plants grow, so therefore they must be tall. Well, that's bullcrud, because that means trees are healthy and they're all healthy. That does not follow. We cannot go down that route. Well, some would say, does it grow fast? Well, if it grows fast, and to a certain extent that's true, plants that are not healthy grow slower. But could you say that a plant that grows fast is healthy? That would mean, based upon that, that bamboo is the healthiest plant in the entire world. We also know that is bull. And yet, this is almost what some people are saying when I get this comment. Some would say, well, what about if it's green? Or better yet, what if it's dark green? That's got to be an indication of health. No, again, because I can hit it with iron. I can hit a plant with nitrogen, and I can green up a plant, and I can actually make it more unhealthy by simply putting on too much iron and too much nitrogen. So that's not a good indication art just because it's green. So we cannot use that as an indicator. What about, does it flower? I mean, obviously it's flowering. That's a sign that it's healthy. And again, to a certain extent, all of these are true. It does need to get to the flowering stage. It does need to be healthy enough in order to reach that point. But that would mean that angiosperms are the only healthy plants on planet Earth, because our qualifier is now, does it flower? So we can't go by that route either. Some would say, does it have a good root system? Because if it's got a good root system, it's got to be healthy. And to a certain extent, that is true. But does that constitute health across all plants on planet Earth? Absolutely not. Some of them have very deep roots. Some of them have more shallow roots. Corn is known for having a shallow root. Some trees, for example, can have a taproot that goes down 100, 200 feet or more. So no, we cannot judge just by the root system whether or not it's healthy or not. Some would say, is it grow even? Because if it grows even, then they can harvest it at the same time. Well, that's convenient for a farmer, but that is not a good indicator as to whether or not the plant is healthy, in this particular case, corn. And some would say, well, I know it's healthy because I grow it myself in my garden on my porch, and I love my plants. I sing to them every day. I put them to bed, I tuck them in, and therefore it's healthy. No, that's not a good way to do this either, because that means everything on your porch is healthy. But what about the rest of humanity? Do they have healthy plants? Is there some way that we can measure this without using any of these common indicators for healthy plants? Yeah, there is, and we have a machine for it. The quickest way to determine plant health is to test plant sap with a refractometer. Why? What does this refractometer do? Simply measures the bending of light. It's really that simple. However, what it is it's measuring the liquid that we pull out of a leaf after we squeeze it, and then we measure how much the light bends, which is almost a direct measurement of the amount of sugar in it. Why do we want to measure the sugar? Because that's the end product of photosynthesis. Photosynthesis is the end game for all plants on planet Earth. If they are photosynthesizing well, they are going to have more sugar. If they are not photosynthesizing well, they will have less sugar. And we can quickly determine this in less than a minute. If you're really fast, you can do this in as little as 15 to 20 seconds, but it's going to take you about a minute. And if you're a little slow, maybe 2 to 3 minutes in order to get a reading. And you will be able to tell whether or not you've got a lot of sugar. Is the plant doing well? Or if you don't have enough sugar, the plant is not doing well. All right, what do they look like? Well, we got two types. We have one which is off to the left. That's the one that's it's not a digital one, and you simply lift up the little plastic piece which is off to the end of the right. You put down your 2 or 3 drops, put it back down, squashes the drops. You look through the eyepiece which is off to the left. Boom, you get a reading. It can be done very, very quickly. However, you can go faster. And the digital model will allow you to do that. That's what I have. So the digital model not only is faster, it's easier to clean, but you can put your 2 to 3 drops in that little well, which is near the top of the image, and then you just press the button, and boom, you get a reading in about a second, sometimes less. And what's really important to me too, being the dumb scientist and the nerd, is that I can tell the difference between 12.2 and 12.3, which is totally and absolutely irrelevant for anybody's needs. But I just think it's neat because, when you get things to the 10th, you just feel like you're doing something more important when in fact you're not. But these are brix levels. Brix levels is what we are looking at, which is a measurement in no small part based upon sugar. Because when you're measuring this, you're measuring the total dissolved solids, but the vast majority of this is sugar. And so you are looking to get the brix levels as high as you can. The brix levels are simply named after Dr. Brix, who came across this way of measuring sugar levels in part, and that has allowed us in order to measure brix levels as well. So we simply name it after him, and therefore we discuss things like leaf brix, root brix, and various other types of brix. And that's what these machines do. For those of you who are technologically advanced, you can get the digital model because that involves batteries. If you are not comfortable using batteries, then you need to stick with the one on the left because that requires no batteries whatsoever. So where do we go with this? When we're testing leaves or plants, we can actually squeeze it. I get it. We can test it on the refractometer. I get that too. But why are we doing something like that? Well, that's because we have insects that eat plants. And I just got finished telling you that they're only going after the unhealthy plants. So I've got grasshoppers eating plants. I've got aphids that are sucking the juice out of plants. What is going on here? Are these all the same? Can we group them all together and just kind of get an idea as to how much brix we need? Some people would say yes, if you check out the internet, because they've got this magic number of 12 brix that people feel you need to get above. As I'm about to show you, it's not that simple. But no, insects are not all the same. And there is a big difference between grasshoppers and aphids. Let's take a look at the digestive systems to get an idea. The grasshopper has a digestive system, which is essentially a tube starting at the mouth. Food is taken in and it passes through the digestive system out the back end in the anus. It's a unidirectional process, very similar to what you and I have. Not so with the aphid. The aphid can take in food and it can be unidirectional, as this is kind of showing. However, it has a bypass mechanism. The digestive system actually folds back upon itself, which is in and of itself weird. This folding back allows it to absorb nutrients before it actually makes it into the aphid. And so what is it pulling out? It is pulling out water and sugar, and it's pulling out as much water and sugar as it can. And it doesn't want to deal with too much water and too much sugar because it can only pull out so much water and sugar. And this system of pulling out water and sugar is called the Homopteran filter chamber. It's simply named after the suborder of insects called Homoptera. It used to have order status, but it's now suborder now. And this includes the aphids, among other homopterous insects. And so they are extracting water and sugar so that they can get various other nutrients out of what they are sucking from a plant. This is fundamentally different than what the grasshopper is doing. And this kind of gives you a little bit of an idea of how insects are doing things a little bit differently, maybe a lot of bit differently than what you and I are used to. And they even differ from one another because these two insects, the grasshopper and the aphid, do not go after the same type of plants. Why are they not going after? Let me give it a little bit of a background right now. Here's a representative nucleotide. I've just got 33 amino acids. Each amino acid is represented by a very simple rectangle. I do have some blue ones and I have some yellow ones. This particular nucleotide or short protein has 33 amino acids, and that's what the complete protein is. So what, you say? Well, this can actually be broken apart. So we have enzymes that will actively break apart a protein or a nucleotide, and they can separate, let's just say, the blue rectangles from the yellow rectangles, and we've now separated this particular nucleotide into two parts. This is partly called digestion. When we digest our food, this is accomplished by enzymes. Enzymes break apart the food. These enzymes are not usually well formed. I've got an amorphous structure off to the right, just showing a very ugly looking enzyme. However, this enzyme becomes well formed in a very attractive looking rectangle, even changes its color, as soon as it gets the addition of, in a hypothetical way, manganese. When manganese, a cofactor, is associated with this enzyme, it becomes active. In our hypothetical situation, this hypothetical enzyme is able to break apart the bond, therefore separating these two. And this is accomplished with the help of manganese in this particular case. This is not always the case. Sometimes we're trying to synthesize things. And if we want to synthesize things, maybe we actually want to make a bond rather than breaking a bond. So sometimes these cysteine bridges form in proteins. Sometimes it's called a disulfide bridge because the two cysteine molecules have a sulfur atom associated with them. And they form this bridge, which allows the protein to contort and twist and do whatever it needs to do in order to make it an active form. So these are all formed from cysteine amino acids. The yellow atom is yellow right here, and they would then come together at that point in order to form the disulfide bridge. Let's just say in this hypothetical situation, we have an amorphous enzyme, but now it gets a cofactor of zinc. Let's just say that zinc, once it becomes attached to the enzyme, becomes well formed and is allowed to now form this particular bond, a disulfide bridge. So you get a little bit of idea of how to make bonds and how to break bonds. And now we have a more or less complete protein, a red blood cell, which is composed of not one, but 4 proteins that are all twisted and contorted and come together to form an individual red blood cell. If they do not twist and contort and come together just the way they are, we have what is known as an incomplete protein. These incomplete proteins are malformed. They're not formed the way that they should be. This one is well formed. A malformed one will not be, and it's these incomplete proteins that the insects go after very selectively. So what do I mean by this? Well, they can't eat complete proteins. They can only eat dissolved nutrients. What exactly are dissolved nutrients? Well, if you've ever been to the hospital before and you've had an IV connected to you, you've probably had dissolved nutrients, because not only do they have a lot of water in there, but they often include amino acids, broken apart proteins, and they also usually put in sugar too, and they pass this into your blood. You will notice that there's no pizza slice in this bag. You'll also notice there's no cheeseburger in there with pickles and lettuce and all the condiments that you might want to put on it. They have broken apart, dissolved nutrients in this bag. Why? That's the only thing your blood can take. Your blood cannot handle a piece of pizza, and it cannot handle a burger. That has to be taken in through the mouth and into the stomach. But into the blood, we can take in dissolved nutrients. So you're now starting to understand how even parts of our body need dissolved nutrients, just as insects need either dissolved nutrients or partially dissolved nutrients. So let's move on to a well-known example, and that is sugar. So here we got some sugar molecules right here. It's a 6-carbon sugar. We've got 3 of the main types. We have fructose, galactose, and glucose, 3 of the most common 6-carbon sugars that are out there. These are known as monosaccharides. Saccharide has to do with sugar, and mono just means that there's one. Therefore, these are all monosaccharides. Well, you can combine them. And when you combine two monosaccharides, you make what is known as a disaccharide, di meaning two. A disaccharide makes a very well-known sugar molecule called sucrose. Sucrose is table sugar, and that's the sugar that you may put into your, let's say, coffee if you're drinking coffee. And so that is now a disaccharide. It's a little bit more complicated because it contains two 6-carbon sugars. In this particular case, it's a glucose and a fructose combining to make sucrose. Of course, it can go on even further. We have trisaccharides. This just means we have 3 of the 6-carbon sugars that come together. Raffinose is a relatively well-known sugar, and it can get even far more complicated than that. We have cellulose. Cellulose is a bunch of sugars connected to one another, end to end, end to end. Cellulose is not digestible by us. It is digestible by some organisms. Why is it not digestible? Well, for those of you who've taken at least biology, even in high school, you probably know that ATP is formed from sugar. The sugar molecule is too powerful. You can't use it for most of the biochemical reactions. And so therefore what you do is you get the sugar molecule and you break it apart and you make 36 ATP from it. So a single glucose can give you 36 ATP, and that's how this whole process goes. And so glucose is infinitely usable by a human being. And here I am showing you cellulose, which is composed of repeating glucose units, and now I'm telling you, you can't digest it. Why can't you digest it? Because you can't break the bond. There's a bond. You'll see that the bond kind of switches in a sort of weird sort of way with the oxygen in between. This bond, this alpha 1,4 glycosidic linkage, cannot be broken by human beings. This is why we don't eat wood. This is why we don't gnaw on trees. This is why we cannot eat cellulose, despite the fact that there's a wealth of food located in this wood. And if you understand at a fundamental level why we can't eat cellulose, no matter how much of it we eat, then you are now starting to understand why insects cannot eat certain foods. So what is the plant doing? The plant is photosynthesizing. I just got finished telling you that, but not all of it is used for itself. About 40% of the plant's sap sugars, the sugar, the photosynthate, is sent down to the roots and exuded into the soil. Many of you probably know that already. That's the process. This happens every single day, usually at night. A lot of the sugars are sent down. It's not exactly 40%, but just to kind of give you an idea, mostly speaking, the range will be about 20 to 70%. Anywhere between 20% of the sugar to about 70% of the sugar will be sent down into the roots in order to feed the microbes that are an integral part of a healthy plant. So the plant needs to be, and this is why we need a high brix plant, because we need to be able to make the sugar in order to feed the microbes, which then in turn are turning around and feeding the plant. This now brings me to my chart. So let's now fill out this chart. So I think you now all have the background that you need to understand, and let's follow along. If I am now taking the sap from a leaf, which I squash and get a few drops out of, sometimes I have to squash 5 to 10 leaves at a time in order to get 2 to 3 drops, but I will then get a reading, and I'm going to get a reading on my refractometer. That reading is almost always between 1 and 20. Almost never breaks 20 brix when you're dealing with a leaf brix. Pay attention to the top of this chart. I've got leaf brix up there. I'm not talking about the flower. I'm not talking about the root. I'm not talking about the stem. I'm not talking about the fruit or anywhere else, just the leaf. It will almost always be between 1 and 20, barely gets above 20 at best. Usually the plant will disperse the sugars. And so I've got a chart now that I need to fill out between 1 and 20. If I'm getting a brix reading from the leaves between 1 and 2, I know that these plants need to be force fed. I know that they will not survive. I know that they will not make it. Sometimes another day, sometimes they will be dead within a few days, and they will almost never make it a week. Force feeding becomes necessary in order to feed these plants because they cannot feed themselves. So if you've ever been out golfing on a green, you've walked on low brix plants before, and you know what I'm talking about. And you probably know that they are watering and putting down nutrients on the greens 7 days a week. They never take a day off. There is no day off on Sunday for this type of grass. Lots of house plants too are also very, very low, usually because they're away from the sun, and you can get very low readings from them, sometimes below 1. The next group is going to be between 3 to 7 brix. These plants have a fighting chance at survival. They're doing a lot better than the 1 to 2 brix ones, but they're not doing great. And you will notice that they will continue to grow, and they will get big, and they will put out roots and stems and leaves and do all the things that leaves do. But you will also notice that they don't look that good. And you will be able to notice that. Most people can notice between 3 to 7 and say the plant does not look great, but it looks okay. What is happening between 3 to 7? Several things are happening. At 6 brix, the plant's secondary metabolites start increasing a lot. Plant secondary metabolites are what, Tom? Well, they give taste to a plant, they give odor to a plant, they give color, color, taste, and odor are some of the common things that we think of when we're dealing with plant secondary metabolites, not the primary metabolites, such as nitrogen. I'm talking about a secondary metabolite. And these are like the flavonoids and the terpenes and things like that. They do not start ramping up until they hit 6. So what are you trying to say, Tom? Are you trying to tell me that a plant that is below 6 brix has no taste and no flavor? Yes. Yes, that's exactly what I'm saying. If any of you have ever tasted a plant before that is at 5 brix or below, especially at 3, you will notice that it's tasteless. The vegetable will be tasteless. It will taste like cardboard. You will recognize it as tasting like cardboard. You cannot be fooled by a low brix plant. You will know immediately whether you're dealing with a low brix one. And so that's what happens. Things really take off at 6. The plant starts to get smell at 6 brix. When you go to the 8 to 12 section, we've now moved into a different category right now where the plants now have the ability to defend themselves. They have a proverbial sword and shield associated with them, and they will be able to defend themselves very, very well against fungus and insects. Now, the water retention abilities increase drastically in this stage, not the 3 to 7 stage. But once you get brix between 8 to 12, something very interesting happens. You have a lot more sugar being produced, and therefore a lot more sugar is going to the roots. What does this do? Well, sugar is hygroscopic, meaning it absorbs water. We now have water retention abilities in the soil, not just because of the type of soil, whether it be sandy soil or silt soil, clay soil. I'm not talking about that right now. I'm talking about the sugar. The sugar will absorb the water. You now have massive water retention abilities due to a higher brix plant. That is big because sometimes we're talking as much as 50% water reduction when you're about in this stage. And that's huge when you're dealing with New Mexico, California, Arizona, places where there's not a lot of water, or you may be in the single digits as far as annual precipitation per year. So that's what's going on here. That is really big. In addition, we have insect resistance. Insect resistance starts in earnest between 8 to 12. Why is this happening? Well, it's in part because the plant's secondary metabolites are kicking off. They weren't there to defend the plant. Now that they're there in usually large enough numbers, the plant is healthy enough to take care of itself. Water retention abilities go up. The insect resistance begins. The insects are no longer interested in some of the plants between 8 to 12. Now, what happens when you're between 12 and 20? Well, they're objectively healthy. Objectively, not subjectively. They're objectively healthy. No matter which parameter you use, whether you're doing a soil test or a plant test, you're going to be able to get very healthy signs from a plant that is between 12 to 20. Food is now produced. We are now producing food that we can consume to give us a long life so that we can live to 70, 80, 90 or more. Before that, spending time eating snack food is not going to usually give us a long life. But we've now got food being produced that is now fit for human consumption. And we have no insects and no disease on the plants anymore. They are unable to eat these plants. These plants are now protected. They have complete proteins. And so we've now got an objectively healthy plant with no insects, no disease, that actually produces good tasting food. This chart is where a lot of the discussion starts and ends for a lot of people. So what do plants need in order to be high brix? Well, this is the no duh slide, and that is they need sunshine, duh. They need water, double duh. They need air and they need nutrients. Now, people look at this and think, why are you telling me this? I know this already. I'm now going to tell you that most of you do not know this, especially if you're farming. Are you getting enough sunshine? Most of you would say yes. And I would say, you're probably not, because low light levels for both visible and invisible radiation are very commonplace among plants. They are not getting enough sunshine. They are being covered due to high density planting. They've got something over them, like the house plants I talked to. You're going to have a low brick situation if they're not getting enough sunshine. They need room to grow. Water, we need enough. If we don't have enough, the microbes have nothing to swim in. And you've got a lot of microbes that are going to go into a quiescent stage, and they're just going to hang out until the water comes back. If you don't have enough, you have nothing to swim in. If they have too much, that's also a problem, because the aerobic microbes will then drown. So if we have flooding conditions and it's long enough, a lot of the aerobic microbes will drown and they will have to come back if the flooding is bad, such as we sometimes get in Florida. When a hurricane comes through, we'll have a fair amount of death of the aerobic microbes, and then they have to come back over time. So water is a huge problem that many people do not consider as often as they should. Air, they don't have enough. You don't have the proliferation of aerobic microbes, and you want aerobic microbes. Aerobic microbes should be about 80% of your microbes. You need some anaerobic microbes in order to start breaking apart that layer underneath, the compaction layer that is underneath, that doesn't have enough oxygen in it. That's their job. Let them do their job. But the aerobic microbes, that's where most of the rhizosphere is located, and that's where they need to do their action. So air is important. And finally, we need nutrients. What type of nutrients? You're talking about N, P, and K? No, 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 no. I'm talking about all of them. Even the obscure stuff like cobalt. All of that stuff has its importance. And that's what gives you a high brix plant. Well, what gives you a low brix plant? Please tell us, Tom. Well, let's start with insecticides, fungicides, and herbicides. All of them will very reliably lower your brix readings. Why? Because life in the soil is dependent. The soil needs to have microbes in it. The plant needs to have these microbes, and you cannot be killing them. So if you have an herbicide, what is it doing? So you put it out there to kill weeds. I get it. You get it. It's in the name. But the side effect is that it kills microbes. Fungicides, what do they kill? This is not hard. Fungi, that's the target organism. What's the side effect? They kill microbes too, including mycorrhizal fungi. Insecticides, what do they kill? This isn't hard. Follow me here. They kill insects. That's the target organism. What's the side effect? They're killing microbes too. So they're killing microbes. This may sound like I'm sounding like a broken record though, but I want to make an important point here. They're not all killing the same microbes. The herbicides are killing different microbes than the insecticides. The fungicides are killing different microbes than the herbicides and the insecticides, meaning if you are using all three of them, you are doing a fantastic job of cleaning out your soil of all the microbes that are needed in order to get the micronutrients into the plant in order to give you a high brix plant. And that's not even the end of it, because it gets much worse than that. Why? Because I'm an entomologist. And so I'm going to talk a little bit more about insecticides now. We have chlorinated hydrocarbons. We have carbamates. We have synthetic pyrethroids based upon the original pyrethrum from the chrysanthemum plant. We also have organophosphates, sometimes called OPs, and we also have neonicotinoids. These are some of the 5 major groups that have been around for decades. Neonics is an abbreviation that we use for the last ones, and each one of these kills different microbes than the other group. And what are you told to do? Well, you are told to go out and spray usually at least 3 different insecticides in order to stave off what in insects? Resistance. So by using 3 different insecticides, so now you're using a carbamate, an organophosphate, and a neonic, Each one is doing a good job of cleaning out the microbes, and then you substitute another one in, which starts killing other microbes, and then you substitute a third one, which kills even more, and then you go back and you start doing it again by revolving it, not to mention the fungicides and the herbicides that you're doing, and you're doing a wonderful job of lowering the brix readings in your plants, which will bring in insects and fungi, among other things. Another big problem, high salt fertilizers. Why do I say that? Well, I think we know that salt and plants do not mix well. We know from history, we know from at least 3,000 years ago, from the Bible, that's where we get this, is that 3,000 years ago, when you conquered a people, what did you do? After you conquered them, you spread salt on their fields. Why? So that they couldn't grow anything, they couldn't recover. They couldn't start making babies and then come back and attack you in 20, 30, 40 years. You essentially decimated them. You beat them, and then you beat their soil by putting down salt. And yet, what are we doing? We're putting down high salt fertilizers. So anytime you're dealing with an NPK fertilizer, most of these are high salt fertilizers. There are a few exceptions, but for the most part, they're high salt. Why? Because they explode, and we don't want them to explode. So we have these nitrogen plants that we have accidental explosions in. We don't want to be dealing with explosive material. So what do? We combine it with a salt. It's usually sodium, not always sodium, but generally speaking, it's mostly sodium. And so by putting sodium with the N or the P and the K, what we do is we essentially prevent it from exploding. Therefore, we make it much safer to use. All of these salts are being put into our soil in very large amounts. So NPK fertilizers are a big problem. GMO plants, also a big problem. They are notoriously low. I'm still looking to see whether or not I can find a good GMO plant that is going to give me high brix readings. Haven't found them yet, but haven't given up yet. GMO plants, why do I mention those? Where are they on the chart? Well, the GMO plants never get above 10, and they're usually much lower. So these GMO plants are a problem all the way around. They have unhealth breeded into them, I have found out. So this is very difficult. I can't even recommend them anymore. Of course, they were fantastic when they first came through. They're like, oh, human ingenuity, look at what we've done. But they're unhealthy. And so by using them over and over again, we've now created problems for ourselves because they can't really get above 10. I always joke with some people, and I'll use that joke now. So I do know a particular individual, fellow consultant, who said he got up to 12 for the GMO. And I said, like, dude, that's awesome. How did you do that? And he said, we went at it hard. We started putting down, lots of nutritionals, and we got it up to 12 brix. And I thought, I'm impressed. And I said, so are you going to do it again? What are you going to do? The farmer? What's the story? He goes, oh, no. We're never going to do that again. I said, why? I said, that just sounds kind of cool that you did that. And he said, too expensive. I would never do that again. He says, I'm not doing it again. The farmer's not doing it again, but we pushed it up to 12, and that's what we got. And right now, if the highest you can get is 12 by putting down massive nutritionals, then you're in pretty bad shape, because I contend that you really need to be about 14 and above before you're in really good shape with your plant. So GMOs, what about GMOs? Good question. Soybean aphid. Soybean aphid, very well known insect. We all know about aphids. Here's a bunch of soybean aphids attacking soybean leaves. And this is something that we've been familiar with for several decades. Why are we familiar with this? We shouldn't be that familiar with it, partly because, or maybe we should, because Chinese records state that soybean was dated back to the 11th century. What that means is that soybeans have been around for a really long time. Then I've got a statistic that says soybean was introduced to North America in 1765. What that means is soybean has been around for, over 200 years in the United States. Take home message, soybean has been here for a really, really long time. Matsumura described the soybean aphid in 1917. Take home message, the soybean aphid has been known and fully described in 1917. It's been known for 100 years. We know that it's out there, but it wasn't doing anything. for a long time. GMO soybean was introduced into the US in 1996. The soybean aphid first discovered on soybean in 1999. It took 3 years for the soybean, which was just a nothing insect. It was just an obscure insect that was described in 1917, has now become either the first or the second or the third greatest soybean pest in all of the states of the Union that are raising soybean. I think most of them have it listed at number 1. So this soybean aphid is attacking in no small part a lot of the GMO soybean. It does not attack as readily the non-GMO soybean, and we can see that we have created a problem for ourselves. Well, what exactly is this problem? Well, here's a little bit of the insect olfaction stuff that I do. I've been able to take a look at the GRs, or the gustatory receptors of the soybean aphid. There are a total of 61 of them. I'm able to combine them all into a single spectrum, and I get to see what the soybean aphid likes to, what is it like to taste. And so over to the right, we have a number of peaks, which are kind of set off by themselves at 41,000, 73,000, and 89,000, but I don't want to talk about those. Those are just water peaks. I'm not worried about those. It's the ones to the left that I'm more focused on. And we can see a number of peaks over in the 3,000 range, but all of you, I'm sure, are looking at the biggest peak, and that's the 10,476 peak. And I kind of want to know what that peak is too, because it's the biggest one. So if this is what the soybean aphid is tuning into, I kind of want a little know a little bit more about this peak. So I start taking a look at spectrums because I want to find out what is it doing. And I find the ammonia infrared spectrum. The ammonia infrared spectrum has a single needle nose peak, ran at about the 3350 wave number range off to the left. And then it has some minor peaks off to the left and the right of it. Not much going on there. Then we have another needle-like peak here at about 1600, 1650 wave numbers, as well as a number of absorption peaks on either side of it. So that's more significant than the one off to the left. And then we have a really big one. We have a really big one over here, to the point where we actually have two needle peaks, not just one. These two needle peaks are just below 1,000 wave numbers. And these are obviously the biggest peaks in the entire graph. And so I've got not just one, but I've got two. So I find out what the peaks correspond to, and then I look to see where the middle of these two needle nose peaks are. And I find out that the middle of them is located at 10,471 nanometers. And so immediately a small gasp comes out when I realize, oh, wow, 10,471 nanometers is kind of similar to the major peak in the soybean aphid. So now I've got a connection between the soybean aphid wanting ammonia in the plant, possibly in large amounts, because I've now got a correlation with ammonia in the spectrums. And this is some of the things that I do. And so I look at this and I said, this is good information to add, but can I go a little bit further? And now I want to take a look at what is going on inside the plant itself. So I take a look at the soybean plant, and I wanted to see what's going on in the phloem tissue. And so when I take a look at the phloem tissue, I see that there should be an ammonium concentration in soybeans of about 10 to 30 parts per million. But I don't find that in the soybeans that we've taken a look at. Unless you think that I'm cherry picking my data, please notice that I've got an N of 741 soybean plants down here. So there's a lot of data that is represented. And the average amount of ammonium inside the soybean plant is coming in at 471.1 parts per million. Far, far above 10 to 30 parts per million. Way above 30, way above 10. We're totally outside the range right now. These soybeans have an ammonium problem. The soybean aphid is keying in on this ammonium problem. And we've now got strong evidence to support it. So these are just some of the things that I do. And I'm just trying to give you some evidence to show that there is some good stuff to back all of this up. And another problem with lowering leaf brix are the greenhouse plants. And this is partially because they're covered. I'm sure you're looking at me thinking they're not covered. We've got them in glass. We either have glass or we've got plastic. So I don't know what you're talking about there, Tom. This is just crazy stuff. I say, no, they're covered. All plants grown in a greenhouse are UV deficient, no exceptions. There is about 98 to 99% absorption of UV in a greenhouse. When we go in there, we will see problems with UV deficient plants, meaning they will be low brix. They're always low brix inside a greenhouse. There are some exceptions, as there should be, because sometimes you can actually remove the roof and open it up and sun can actually get in. And at that point, you're getting a little bit of cheating going on. The sunshine will come in and it will actually health up the plants. They will get a higher brix if you have one of those removable roofs or sliding roofs. Not everyone does. And believe me, the first chance the plant gets, if it can, is it's going to get out of that greenhouse and it will grab as much sunshine as it can. It's first chance it gets. And so once it does, the brix readings go up immediately. So this one is already sticking a branch out from a broken greenhouse right now, and this is what we see. So greenhouses are a problem. They're UV deficient. Why do I say that? Well, let's take a look at the amino acids again. I talked about them briefly during the presentation. Now I've got about 20 amino acids. Sometimes there's 21, depending upon how you want to look at them, but I've got 20 amino acids listed here. I don't want to talk about all 20 of them. I just want to talk about 4. I want to talk about phenylalanine. I want to talk about tryptophan. I want to talk about tyrosine. And I want to talk about cysteine. I did talk about cysteine earlier on, if you remember, making those cysteine bridges. Just those 4 I want to talk about. Why do I want to single out these 4? Because these 4 are UV detectors, and they're very good at pulling in UV. They have certain functions that are associated with this process. As a matter of fact, we know so well how well they actually hold on to UV and how much they absorb it, but we have numbers for it. 5600, 1420, 197, or anywhere between 250 and 320, depending upon various circumstances. So I've got 4 amino acids. And the cysteines, by the way, do not absorb UV. It's only when they're in the disulfide bond that I had briefly mentioned before. Only then do you get a well-known absorption between 250 and 320. So the UV absorption can be considerable in certain proteins. And it's not as high, it's almost close to 0 in the other 16, but there are certain combinations that do allow, we have recently learned, a little bit more UV absorption than just the 4 that we see here. But I do want to talk about these 4. This is important to talk about these 4 because glyphosate kills plants by interfering with the synthesis of the essential amino acids tryptophan, tyrosine, and phenylalanine. Please tell me that you're seeing the connection in this slide right now. Glyphosate is actually creating plants that are attracting insects very similar to what they are in a greenhouse. And you will notice in a greenhouse, you get very specific insects in a greenhouse. They are all attracted to the UV deficient plants or the glyphosate plants, such as the aphids, the white flies, and things of that sort. And they will come in and they'll start sucking on the plants because they are weakened to the point where they can actually eat them. That's the point that I wanted to make. And so now I need to tell you about these different groups. These groups include different insects because not all insects will be attacking a plant that is low brix. They all have differential abilities to do so. So the aphid group is where we start out at. If I get plants that are running 6 brix, which is not good, aphids will start to move off the plant at just 6 brix. At 7 brix, I get even more, and by the time I get to 8 brix, there are no aphids left on the plant. So between 6 to 8 brix, the aphids start jumping off the plant and they will move on to another plant. The situation changes as you move from one group to another. If we move on to the other sucking insects, such as the leaf hoppers, the frog hoppers, stink bugs, lantern flies, things of that sort, these sucking insects will leave a plant once it reaches 7, 8, and finally 9 brix. It'll all depend upon the species, but that's a 2 brix range, depending upon the species, that they will start actively leaving the plant. Chewing insects do much better. They can handle plants up to about 9 brix. Once you get to 9 brix, chewing insects start to lose interest in a plant, and they will start to selectively leave the plant at 9 brix, 10 brix, By the time you get to 11 brix, there are no chewing insects left, with the exception of the grasshopper group. Very, very annoying group, which I have found feeding very briefly on 12 brix plants. They do take a few bites. They don't like it. They move on, but the grasshoppers are quite annoyingly good. And so the grasshoppers include the katydids. They also include crickets and things of that sort. And this grasshopper group will be dealing with higher brix plants. So as you're moving down the process, you can actually change the insects that you are actively attracting to your particular plants. And I have actually gotten excited when people tell me saying like, oh no, I don't have aphids anymore. I've now got caterpillars attacking my plants. And I'm like, oh, that's awesome. Congratulations. They're looking at me like, why do you have to be so difficult, Tom? And I said, well, that's because you just moved up 2 feeding levels right now. So you're on your way to health, but you're not there yet. So keep going. Doing a good job. So let me give you a few pictures to show a little bit of what this is all about. Some of you may be asking too, because this is a question that comes up and I deal with this in the other presentations. Well, what about a tree? Can a tree have any brix readings that are at differential points at different points of the tree? Absolutely they can. Will the insects be differentially attracted to those different parts of the tree? Absolutely they will. So here we got a tree. You can see it's bifurcating, probably about 6 feet up. It splits off into 2 branches. Let me zoom in. This is a zoom in on that. You can see the left side is dead. The right side is doing quite well and is putting bark on the outside. And what do you see off to the left side? You see a lot of woodpecker holes. Those woodpecker holes are going after cerambycid and buprestid beetles. They love these larvae because they're big and juicy and fat, and they love to eat them, and it gives them a really nice meal. But you'll notice that the woodpeckers are not attacking the right part of the tree. It's the same tree, but they're only attacking the dead part, which goes back to my thesis that I mentioned earlier on. So here we got another situation. These are the cerambycid beetles, longhorn beetles. You may have seen them before. Here are this is an emerald ash borer, which is a buprestid beetle. It's kind of bullet shaped. And we have the same thing going on. I don't know what's in here. It could be cerambycids, could be buprestids, doesn't matter. But this branch of this tree is riddled with woodpecker holes because they're going after the larvae of the cerambycids and the buprestids. That's what they do. This part of the tree is dead. The left part of the tree is live, and we get obviously different brix readings from them. We're obviously going to get nothing from the right side because it has no leaves, but that's the point that I'm trying to make during this process. And so here we've got just one. I mean, I love this, but while I was at the ESA meeting in San Diego, there's this talk, living with the emerald ash borer. Larger, older trees are attacked first. Well, this is what I've been trying to tell you for the past hour, is that unhealthy trees that are starting to go downhill are attacked first. The emerald ash borer is going after what? It's going after ash trees. The ash trees have been around for a long time, and we hate to lose them. I get it. I understand, especially if it's been in your family for a few generations. My mom and dad and my great granddad, they planted those ash trees when they came over. Well, ash trees, depending upon the species, usually live anywhere between 150 to 250 years old. Most of the ash trees in the northern part of our country are between 150 to 250 years old. Many of these trees are simply dying. It's okay. It happens. The emerald ash borer is moving in, taking out the tree, as it should be. And so we get people right now who now see an emerald ash borer attacking a tree, and will take a chainsaw and will completely take out all the trees within a 50 to 100-foot radius of that tree, even if they're healthy and even if they're not being attacked. We have killed far more, it's not even close, far more ash trees with our chainsaws than the emerald ash borer has. So take a good look at those figures about how many ash trees we have missed and lost, and know that most of the fault is our own. We also have tephritid flies like the Mexican fruit fly, Anastrapha ludens. These particular females are laying their eggs inside fruit because they're a type of fruit fly, not the same type as Drosophila, but they belong to a different family of Tephritidae, and they're laying their eggs inside. Well, is this any different? Well, no, we still measure leaf bricks though, but these flies have determined that this fruit is unhealthy, and that's why they're laying their eggs in it. The same thing goes over here. We got another tephritid fly. This one, Ragoletus indifferens, is the western cherry fruit fly, and they've got 4 larvae feeding on the inside of a cherry. So these eggs have obviously been laid inside and they're eating happily away. Every one of us knows that this cherry is coming from a low brix plant. You know that because you've listened to me for the past hour, and you know that the insects are only attacking unhealthy plants. But there's a little bit more to this. I've been doing this for a while, and there are some other indications. And I also know that this is unhealthy and it's low brix because I don't see a white line. I don't see a white ring. Do you see a white ring? I don't see a white ring. To me, it just looks like a bunch of red mess. So when I'm looking at a cherry, I need to be able to see a white ring around the pit. When I see a white ring around the pit, I know that health is starting to be imparted to the particular cherry on the cherry tree. Here we've got a lots of white. This is mostly calcium, but it also includes other minerals that I talked about before. You know the minerals? Those same minerals that the microbes are getting inside the plant. Those same microbes that are putting in cobalt or copper or iron or anything that they are feeding to the plants, these minerals need to show up inside the plant or inside the fruit. And here's a physical manifestation of them inside the cherry, where we've got a white ring, which sometimes it's a little stronger than others. If it's a little stronger, you will have a higher brix from the fruit. And so the same thing goes with grapes. So here we are looking at some grapes right now. Take a look around, just around the edge of the grape. Right around the edge of the grape, you will see a white ring. It is not necessarily around where the seed would locate it, a little more central in the cherry. This one is a little more towards the tip. This is where you find the white ring on the grapes. And you can tell whether or not you're dealing with a 24 brix grape, which is going to be fantastic for winemaking, or whether or not you're dealing with a brix in the teens, which is probably going to end up as a table grape. For those of you who can't see the white ring, I can show you it's a little bit more pronounced. The higher brix you get, the more the white ring becomes evident. If this white ring is discontinuous, it's low brix. If it doesn't exist at all, it's low brix. If it's there, the brix is starting to go up and we can tell. And if it gets really, really thick, as it sometimes can in some of these pictures off to the left, where the white ring is relatively thick and easy to see, that is the manifestation of mostly calcium, as well as some of the other minerals, which are usually whitish or kind of a silvery nature. And they're being deposited in the fruit. And so here we're taking a look at grapes. These are not healthy. You can tell just by looking at the outside. We can see that it doesn't have a beautiful green shine to it. We do have some possible symptoms of rust. We open them up. The white ring is not that easy to see. It's not that easy, and therefore we are dealing with a lower brix grape. This is something that you will see on your table. These are the table brix grapes, which are usually in the teens. And so there are other ways of doing it. I absolutely tell you, you need to test it first, though, but I'm just trying to give you a few clues as to what I've been looking at for the past quarter of a century. And so we do have these, stuff that comes out about the picture wing flies, the tephridids, attacking maize. And there's a quote from this, and this says, females cannot penetrate intact plant tissue with their ovipositor. In most cases, they deposit eggs into damaged, cracked, or decomposing plant tissue. What a great quote to pretty much end this presentation on. So that's where I am right now. So this information is out there. It's not new information. It's essentially old information that I can say that I've resurrected, that I've had to add some science to so that we can understand it a little better. My job was to teach you as much as I can in just a little over an hour. I wanted to be able to teach it to you so that you can understand better rather than me just getting up there and telling you that they're only going after healthy plants, and then you walk away thinking, I have no idea what he's talking about. This makes no sense whatsoever. So for those of you who wanted to go further, there are 3 more presentations. I'm not going into those now, but I'm now going to turn it over to some questions, and I will be happy to answer all questions until we run out of time. So I think Carla is going to be heading the show.
Yes.
Okay.
Yeah,
All right.
I will present the questions and we will go from there. Uh, uh, Dr. Tom, do you mind stop sharing your screen, please?
Absolutely. Done.
Okay,
Thank you.
thank you. So everyone is in awe. I think that we need a couple seconds to kind of understand where we are now because you blowed everyone's mind. So thank you for that.
You're welcome.
And our first question is from Jean. Is there any published data to support the brix level and pest resistance? I would, I've only found, sorry, two articles on Google Scholar that addressed this,
Mhm.
and both found no correlation between leaf brix levels and leaf hopper numbers in vineyards.
Absolutely. Yeah. This is the one article which is brought up more than any other article because this is the only one that's published. I'm not allowed to publish, as I mentioned earlier on. And so are there any published articles? This is the only one that was published. It's one of the worst articles I've seen because when you're comparing low brix with high brix plants, you're going to need high brix plants in order to compare with low brix plants. There's some common sense that you need to pull in here. If you take a look at all the brix readings on that particular article that was written, you will find that the brix levels are all very low. Most of them are below 8. I think there might be a few that get up to 10, but they're only dealing with one really insect, and it's going to be the leaf hoppers. They're not looking at the insects across the full gamut. They also have no brix levels that are high enough in order to see whether or not they're being attacked. They don't have anything between 14 to 20, which would be a good figure to say, okay, there's no insects attacking it. They didn't have any, so therefore we don't have a valid comparison. And if you also take a look and read that article in detail, you will find that a number of the vineyards there were spraying insecticides. So if you are measuring the insects that are attacking your vineyard while killing them, you have essentially taken out the ruler. You've taken out the meter stick. Because if the idea is to measure whether they're present or not, and then you spray with an insecticide, you have now disqualified yourself as to being able to effectively determine, let's say I've got a 17 brix plant versus a 3 brix plant. Let's take a look at the difference, what insects are attacking them. We have not seen that. I am now sharing with you, as I've done in the past hour, more information so that you can understand this better, and that we're going to need better articles than the one that was published in the 90s from the University of California, and that's the one that is often pointed out. There are additional problems with it. I spent way too much time attacking it in presentations in the past. I've now stopped because it took me, I think, 7 to 10 slides to be very comprehensive about it, but I just hit a few salient points.
Yeah, I mean, we always reach that point that can I just struggle them? I don't have that time anymore. So thank you, Tom.
You're welcome.
So our next question is from Nicola. If a if a farmer is growing a monoculture, for example, corn, wheat, and if the crop is healthy, can it avoid pest damage, or does monoculture always create pest problems?
If it is healthy, the insects will not attack it. We know this because farmers keep planting plants. There's a part of me that just wants to end at that point because they keep planting. If they're going to lose their crop, why keep planting monocultures? But they keep doing it. And so right there, that tells you that their plant does not get destroyed. They usually get a return, may not be as high as they want, but they get some return. So if their plant is healthy, even if it's in a monoculture, you're going to be just fine. Now, does a monoculture often bring in the insects? Sadly, it kind of does, because usually when you're dealing with these monocultures with 10,000 acres of corn, you don't, it's usually GMO corn, among other things, mostly. And because of this, they're usually spraying, trying to protect it, and problems come out, and then you have problems with the insects and the fungi too. So yeah, monocultures often do create problems, but you can raise a monoculture without having to deal. For example, there are some places in the world I've heard that have for I think 1,000, 2,000 years been raising corn on the same plant, same plot of land. pretty much nonstop without putting any nitrogen down. And so we know that there are ways to do it. We just are certainly not doing it now. So no, you cannot disqualify something simply because it's a monoculture. And if they are healthy, the insects will not attack it. Yes. Great question. I get that a lot too.
Dr. Elaine and Dr. Adam, I'm just driving to Tom, but if you want to chime in, just open your mic and go.
Hit me hard, guys.
So next question is from Chris. Tom, you refer to relationship between healthy plants and insects. Does this relationship also work for other creatures such as slugs and snails?
Okay. All right. I love this question. The answer is yes. And then the other answer is I have absolutely no authority to talk about slugs and snails whatsoever because they're mollusks and I have 3 degrees in entomology, so I cannot discuss this question. Let's move on to the next question. However, I kind of alluded to the fact that I do know a little bit more about entomology, so I am going to tell you, yes, we have seen the slugs and the snails attracted to unhealthy plants. Just for your information, they only go after the softer ones. So if you have certain minerals inside the plant that harden up a plant, it will make it impossible for slugs and snails to eat. That's a little bit of a clue. But I don't deal with the slugs and the snails that much. They don't have enough legs. I usually need 6 legs in order to speak competently on the issue. And so therefore I'm now further bypassing the snail and slug question. You're welcome.
I'd love to add something there, Carla. I think it's very easy when you first hear this talk, which I did a few months ago, to think, oh, it's very black and white. But nature and biology is a gradient. And so what happens is you want the plants, as the brix goes up, they're more and more resistant. That doesn't mean it's impossible, especially not if something lands on them that's starving to death, right? And I think I have tried to answer a lot of questions from our community about slugs in the past, because sometimes people are like, I can't get anything to grow. There's all these slugs. I've come up with the same thought as you, Tom, which is maybe there's some mineral deficiency or something that you need to work on. I mean, I grew some plants last year that were silica deficient, and that means they didn't have the rigidity and structure that they needed.
Silica, iron is another big one. Copper is another big one. Boron's another big one. They all add hardness to a plant, and snails and slugs don't like any of that stuff, among other things.
Yeah. And so as we're transitioning, it's also a gradient over time. The soil can get better and better, right? And maybe in 4 or 5 years, things will be really resistant to slugs. But in the meantime, we have to plant a trap crop that the slugs will be attracted to and let them have it. Or we have to use some kind of like even beer traps or something, right? It depends on the scale that you're at. So we can stack different strategies together, understanding that the foundation of everything is a strong, healthy plant with a good immune system.
Well said, Adam. Excellent words.
Yeah, Peter is suggesting in the chat that we should send ducks on their way. Oh, thank you, Peter. Next question is from
Elaine's
Marian.
raising her hand.
Sorry,
I'm
Elaine.
sure
Sorry.
we have to. Yeah.
You're muted. Sorry, Elaine.
I can't hear you, Elaine.
Elaine, you're still muted.
Yeah.
Carla, did you do something to her?
No, I'm trying to unmute her and I can't.
Oh, there she goes.
There it is.
There you go.
That was like 10 times I had to click before it stopped blinking at me and let you hear me. So don't do that. What we found in the world of the soil food web is that the slugs and the slimy critters require a wet, very, very wet ground.
Yeah.
And the water is going to be held right up at the surface of that of the field. And so, you may come along and apply something that'll kill some of those organisms, but how soon does that water revive? It comes back down. It's going to be just as low oxygen condition in the soil as possible. So instead, what do you do to build structure in your soil? And that's going to be get those bacteria in there, but good aerobic bacteria. Same thing with the fungi, same thing with the protozoa and the nematodes. So get a good compost spread out if you want. You can also spray a good compost tea. So you just need to do a little testing on your own properly to find out how much you probably need in order to reverse the unwanted problem organisms before it becomes really bad, and you're going to have to go through and do some punching holes through getting oxygen into the soil.
Yeah.
That's you only have to do it once. If you've done it correctly, you've gotten the oxygen, you've got the microorganisms in that soil, you built the structure, and now you're not going to have a problem typically until Florida has another hurricane.
Till we
Depends
kill all
in
the microbes again. Yes. Yes.
Yep. So even Mother Nature can be mean and nasty and vicious.
Sure can. Sure can.
We should not challenge, right?
Hey, Tom, I have a question. I don't want you to stay on if you have another meeting to go to, but
I
some
don't
of our
have another
students-
meeting, so if you guys
Okay.
need to stop recording in a few minutes, you are welcome to. However, I'm willing to stay online even if you stop recording. I will continue to answer questions.
Awesome. I think some of our students would love to stay here a few extra minutes with
Yes.
us.
Okay, that's fine with me. Yeah, I don't have anything to go to right now. I'm
Thank you
really not
so
as
much.
popular as you think. So
Oh,
yeah,
you are very popular here. We
I
we
don't know
bet
what to do.
280
Fake
guests.
tears,
So
fake tears.
Do you know of many people that have put together this the soil food web concept with the work that you're doing with the brix?
No, I don't know of anybody who's put it together, because there are certain individuals out there like, oh, I don't know, Elaine and Adam, who haven't actually gotten together with people who are dealing with the brix, like, I don't know, me. And so because of that, you would need to get them together, because I don't have a specialty. I mean, you put those microbes under the microscope. I know what you do, Elaine. You put them in the microscope, you identify them quickly. This is what you teach the students to do. I can't do that. I can't tell the difference. And so there's really nothing I can do in regards to the soil food web. However, having said that, I know a little bit of what you know, is that the aerobic microbes is where the action at. These microbes are putting all of these nutrients into the plant. They cannot get them by themselves. They need the microbes to do that. We also know that they're eating the microbes now too. Thanks to James White, we've got that information. And so there's a lot of health that's going on. And when we see this high health in the soil, as long as we have a high health seed, which most of the time we don't have, we then put it in high health soil, we get a high health plant, everything seems to be acting the way that it should, and we get a high brix plant. And it will be high, it will be 14. I can walk out of my office right now and find a 14, 15, 16 brix plant in a very short period of time. It's just out there in nature, they're just growing out of nature. So it's not that hard, and it's relatively easy for me to do. So yeah, no one has really looked at the connection yet. So I think you've now just brought up a collaboration.
So yeah, let's go for the collaboration. Let's work on writing those proposals and figuring out a good place to go to. Especially we're seeing more of a turn of instead of the professors and the scientists, there are more people who want to use what we've been finding. And so working with them, their ultimate goal is to have a product that they're going to be able to sell and have $1 million in the bank.
Yeah,
We're still going to be interested in how did that work and how long does it take. So, let's kick that idea around. It might take us a year or two to put the proposal together, but everybody who's here, think about whether you'd like to learn some of this.
Mm-hmm. We're gonna get there for sure. So let's go for another question. And here we are sending you to the tropics, Tom.
Yes.
Are there any expectations as in tropical environments like Hawaii, where in the past pressure still can affect healthy plants growing in well-managed soils, specifically non-native plants? Any of the familiar Western diet veggies seem heavily attacked in most gardens and farms I observe here.
Okay, stop.
Thank you,
Don't
Maria.
let this
Yeah.
screen go. Stop.
Mhm.
Hold that screen right there. This question comes up a lot. You see the word that was used, seem. Seem heavily attacked. This question comes up all the time. I see this. I see plants that seem to be healthy. They seem to be heavily attacked. This seems to be an exception to your rule. This seems to fly in the face of everything that you've said. Or you can go ahead and let this go right now. This question comes up, but we can take care of this in a hurry by testing it. We can test it. We get a hard brix reading, something that you cannot argue with. A lot of farmers will cry right in front of you when they find out. I kid you not, I was doing a presentation. They asked me to do some brix readings right in front of them at their nursery. And so, you know, you've got these brix readings that come out. I mean, sometimes there's just total silence when you find out what the brix readings are, but there are reasons for all of this. So you test. There are a number of things, as I'm sure Elaine can do as well. You can just look at some soils and tell very quickly whether or not it's going to be good or bad. I can look at some plants and tell very quickly whether it's going to be high brix or low brix, but I still test it. I still test it because I need numbers to work with. I just want to get up there and say, this is healthy because I said so, and expect you all to just believe me because I got a PhD after my name. You know, that's just not going to fly. Everyone knows that. And so because of that, we shoot for numbers, and the refractometer gives us that number. So if the insects are attacking those plants in well-managed soil and the plant is healthy, then they will not attack the plant. There's a problem there somewhere. So, and when you test it, you will find out that the basis of the question is actually incorrect. And so we can get some hard answers, and we can get rid of the word seem, and then you'll have some hard numbers to say, I have some brix plants that are coming in at 6.1, and I have some insects attacking them. What's the problem? And I will respond with, in part, that's because the brix is 6.1.
And then they need to know how to fix that.
Yes.
And then that's the biology in the compost that we put out, or in the extracts and stuff. So
Yeah.
yes, I think we would work together fantastically.
But where are we going to meet? Because I'm in Florida, and
no problem.
I'm in paradise right now. So
you know, Tom, I'm going to be in Oregon, in Corvallis area in August, mid-August. So maybe you just need to take some of that, you know, laboratory money of yours and fly over there, and the four of us can hang out.
yeah, I think they would have to do that. Yeah, because thank you for not inviting me up to Oregon in January. It's being like really bad memories of my past, you know.
And we promise another live session with folks. They are jealous of us now, Adam. So we need to find a way, if this meeting happen live, to may have a live session as well.
Okay. All right.
So
I will not grow my beard for it. I will not grow my beard for it. I just want to say that right up front.
Tom, could I break in here? I saw a theme of questions around invasive plants, invasive insects, and whether or not this sort of broke your scale. And I think in some cases, based off of my understanding, you would have something that's relatively maybe more resistant to the defensive compounds of a plant that it did not evolve with. But that doesn't mean it just breaks it all together, right?
Yeah, if the plant is unhealthy, it'll be attacked. And so when we have a lot of invasive plants that come in here, part of the reason we call them invasive is because they're taking over. Thus the term invasive. And the reason why they're taking over is because they're healthier than the other plants, and they're just spreading, whereas the other plants are succumbing, usually because they're lower brix, and they will then move into our, dare I say, low brix crops. And so this then creates a problem with these invasive plants, but they're generally healthy. Now, we do test the weeds, and I encourage you to test the weeds, because when you have a crop and you have a weed, it's good to see which is higher. because if the brix of the weed is higher, then you're raising weeds. That's what you're doing. You're not raising corn. You're not raising soybeans. You're raising weeds. If the corn or the soybean is higher, or whatever plant you're doing, apples, oranges, and that's higher than the weed, then you're doing a good job. You're raising your own plant, but the weeds will not grow unless they have certain conditions that are met. And those are almost universally unhealthy conditions, because their job, and they do it well, is to health up the soil. And there's some complex physiology and biochemistry involved in that. A lot of my listeners probably know a lot about that already, so I don't need to repeat it, but you would kind of know where I would go if I decided to talk about this at length.
Yep. One more question?
Mm-hmm.
Okay, let's go. So this question is from Debbie. Japanese beetles are attacking our vineyard. Testing bricks by crushing leaves in garlic press and applying juice on refractometer showed a brix of 13. I sent the leaves to lab and report came back deficient in 2026 nutrients and 1.3 brix. Can you explain these differences, or what should we look for when we send those kind of tests? I think that is much more on this aspect. What should we look for information?
Okay, based upon the brix readings of 1.3, I'm going to make an assumption. Very dangerous to do, because you know what happens when you assume. I'm sure a lot of you can finish that sentence, but this is a family show and I'm not going to say what that is. So because I'm assuming the 1.3 brix, that when you sent the leaves away, that you were doing an analysis of leaf. It was a leaf analysis where you're taking a look at the phloem and the xylem tissue, which is extracted from the leaf. That's what I'm assuming is happening right now. Follow me along right now. I crush the entire leaf. You send it away and get just a little bit of the sugar that is in there. So usually the phloem and the xylem tissue contains substantially less because it's part of the whole. This is also explaining the reason why your brix readings are higher when you crush the leaf. So when you send it away, the brix readings that they give you back is not the actual leaf brix. It's the sugar content of the phloem tissue, which is very accurately about 1.3. Sometimes the soybeans, for example, they're averaging 0.69, less than 1%. Many plants can usually run easily 2 to 3. They don't get much higher than 4% in the phloem tissue, because they don't want that much sugar going around the phloem tissue. They control it and they store it. A lot of it is stored in the leaves. Sometimes it's stored in the roots. Sometimes it's stored in the stems. There are different presentations to deal with those different issues. But when you're dealing with a leaf brix situation, that's always going to be higher. Now, when you get a 13 brix, I would say take a look, because usually that's just a little, not much, because I'm expecting them to go to 11 brix, the Japanese beetles. But because it's just a little on the high side, I would say, was it dry? Because if it was dry, and if we haven't had rain, or if it hasn't been irrigated for 3 days or more, the brix levels start to artificially go up a little bit higher. And then we see these jumps in brix that are not real, because the sugar is starting to condense a little bit. So to get a more accurate brix readings, and you're starting to answer questions that I have answered in the second presentation, and the third presentation, and the fourth presentation, is that when you start adding in all of these slight fluctuations, you become more informed about what is going on inside the plant. And so you want to make sure that when you're testing it, it's well watered. If it's had rain the day before, you're in good shape. If it's being irrigated, you're still going to be in good shape. But if it's been sitting there and hasn't had rain for 2 weeks, you will have an elevated brix level that will be artificially associated with the concentration of the sugar solution. So what do you do about this? I've gotten this phone call many times. I got a half hysterical phone call from Canada. Oh, we've got these brix readings that are 13 right now. We've got all these insects attacking it. I don't know what's going on. And so I said, all right, I want you to go out there. I want you to choose a single plant, any plant that you want. I want you to go out there with 3 gallons of water, and I want you to hit that one plant. Do not spread it out on any other plant. I just want you to throw as much water on that one plant as possible. And then I want you to come back 24 hours later and test it again. He calls me back. We're down to 6. Wow, that was awesome. How did you do that? And I said, well, that's just because that's what the plant would be doing if it had a natural amount of the water. In some cases, Sadly, you do have to play that game with the plant. So if you're dealing with a very, very dry plant, and sometimes we are playing that game in Southern California, New Mexico, Arizona, Texas, parts of Colorado get very little rain. You have to be careful about that because you can get artificially high readings. So that's what I think is going on. The Japanese beetles are in there. It's deficient. So you're being told that it's deficient in many minerals. I'm sure that it is, because it's usually many of the minerals that are absent that bring the Japanese beetle in. The brix readings are just a little bit artificially high, and things will change. That is my guess. And again, I've just made several assumptions in answering this question. Very, very dangerous. Is this still being recorded? Dang, it is being recorded. All right, I'm now.
I think we are safe. You said many, many times that's based on assumptions. So
I hope so.
I think we are covered.
But we need to
So-
add soil food web information with what he just talked about, because the instant you start encountering anaerobic root systems in plants, that says to me, go get the compost out and fix the problem in the root system. And then, we should be doing the above ground parts of the plant, the leaves and such. So 2 triggers instead of just one probably will solve those problems. Can't
Excellent
say
point,
for
Elaine.
sure until we have the data. How many times have you heard that?
Oh yeah, numbers. Need numbers. Need numbers. You want numbers.
Yep.
All right.
One more?
Oh, absolutely. Sure.
Okay, let's go. So this question is from John. You talk about aphid digestive system type and grasshopper digestive system type. What about caterpillars? Is there a brix level high enough to prevent them from eating the plant tissue? I saw one of your videos on YouTube 2 years ago, and it was a paradigm shift for me. I can not understand how impactful you have been to my regenerative journey. Thank you so much for your work.
You are very, very welcome, John. I'm happy to offer you paradigm shifts. If you want to know more paradigm shifts, I've got some other YouTube videos out there on insect olfaction. And if any of you are suffering from insomnia, I will promise to cure you from that. So enough about the insect olfaction. Now, if we go back to the paradigm shifting that you're talking about, the caterpillars are chewing insects. They are not in the grasshopper group. Therefore, they fall in the chewing insect group, meaning the chewing insects will leave a plant between 9, 10, and 11 brix. That's usually about the range that we start to see them differentially leave, because not all caterpillars will leave a plant at exactly the same brix. But when it gets to 9, a lot of caterpillars are done. Others have to get up to 10. Others, when you get up to 11, by the time you get up to 11, they're pretty much all gone. There's almost nothing eating the plant anymore except a few. And that is where the caterpillar falls in this particular, because they have chewing mouth parts. That's why I use that chart, because I wanted to encompass. And sometimes it's not super clear because I'm being incredibly general about what I'm saying. During the second presentation, that's where I zero in on a specific insects, specific plant, and I get down and dirty with nerdy Italian, Latin terms. Some of them may be Italian.
Yeah.
And so because of that, this helps open up the mind and realizing that there are specific examples that we can use in order to back this up. But for this presentation, if you haven't noticed, and I'm sure you all did, I kept things as general as I possibly could. Only Adam among us right now has seen the second presentation, where I started getting very specific, when I started getting into very specific details about where this is going. And so he has seen a little bit of what the next step is. But right now, I wanted to do umbrella. I wanted to give an umbrella presentation where I covered everything without exception. But there are some exceptions. No one has brought up the praying mantis, because that'll pretty much grab anything that moves. But for those of you who don't know, the praying mantis is very closely related. It's an orthopteroid, and so therefore it's very closely related to the grasshoppers. But there are those exceptions. I am talking about the plants, so no one brought it up, so I brought it up. I love the praying mantis, but generally speaking, when you're talking about insects and plants, I have painted a broad enough picture that encompasses everything of all the insects attacking
John's still
all
on
of
with
the
it,
plants.
muted.
Okay.
Awesome. So one more question, and I
Sure.
think this is I mean, at least among our students, is a common question. In case
Okay.
of hardleaf plants where it's not possible to extract clean sap with cut leaf cells that alter the brix count, but it's easy to extract sap from the petiole, would the leaf petiole correlate with Dykstra leaf charts?
Do they correlate? Thank you, Danny. Do they correlate with the leaf charts? No. No, they do not. Because when you're looking at the petiole, you are dealing predominantly with the phloem and the xylem tissue and just a little bit of vegetative substance around it. They're going to be the epidermal cells which surround it. And you have a little bit of chlorophyll going on, but not a lot. Anytime we measure, if we take a leaf measurement and then we put it next to the petiole measurement, so we can get, make it up, 30, 40 petioles, put them in, crush them. And then we take out, let's say, 5 to 10 leaves, crush them. We got 2 or 3 drops from the petioles, 2 or 3 drops from the leaves. We always, 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 said that for emphasis, get a lower brix reading from the petiole. Why? That's because the petiole is not storing the sugars. I want to know how much sugar is being produced by photosynthesis, because that's what the leaf does. I also want to know how much is being stored in the leaf. And this total figure gives me an idea of a true reflection of the health of the plant. I cannot get that from the petiole because there's so little storage that is going on in it. And therefore, I never use the petiole. Anytime I get a leaf, I cut it off. I make sure that there's no petiole part at all, that I'm just dealing with the leaf, and I measure just the leaf. Great question. Great question.
Yeah, awesome. I guess Dr. Elaine had to leave for a meeting. If I could kind of stress a little bit my lip reading skills. So, Tom, let me know when you need to stop because we have a bunch of questions coming on your direction. So,
Yeah, I'm afraid to tell you that
Mhm.
I've got time. So yeah. So I mean, if there aren't any students, I'm sure the students are dropping off like flies right now. So if they are, I'm sure the numbers are going down, down, down. Adam, could you let me know when we get down to 3 students? At that point, we'll probably just kind of, stop it at that point. And
Okay,
I'll know that that's it.
we're about 200 more than that right now.
Yeah.
So
Take a
Okay.
deep breath, Tom.
Right.
One common question that it's permeating in a lot of other ones is, do you recommend any video material readings for people to understand how to use the refractometer and adjust all this beautiful knowledge you shared with us today?
I don't think I understood the question. Could you repeat that again?
Yeah, sorry. They want more material on how to properly use the refractometer.
I got it.
What do you
I see what you're
suggest?
saying. I see what you're saying. Okay. That is included. Yeah, that's in the other presentations. I do bring up the instrumentation. I talk about it. In addition, as Adam notes, I also travel. So not only was I giving presentations with Adam, best experience of my life, but also I had the opportunity to bring my equipment with me, and then I demonstrated the equipment, and then we took a look at a few leaves so people could see what I am doing. So I do have presentations that will talk about it on a video sense, and then I actually travel. I've got a trunk with me, a big trunk that they usually put musical instruments in, but it works out really well for transporting delicate equipment. And then I will actually go and I can demonstrate the stuff for you, because that can take a little bit of time. It's not easy to collect the leaves, put them in, and if you do a video presentation, I'm just going to put everyone to sleep, and I'll lose everyone at that point. But generally speaking, I'm just going to tell you in a couple seconds, put as many leaves as you can on a garlic press and squeeze the bejeebies out of it. If you can get 2 or 3 drops out of it, you're in good shape. If not, I use the plant sap press. I have a plant sap press that I use to squeeze out leaves when I've got a lot of them and I'm in a hurry. And that's what I will do when I'm doing that. So that's more when I have to do multiple readings during a day. I'll go out there with my plant sap press. I just pass on the garlic press completely and utterly. I still use the garlic press for fruit brix, because it's relatively easy to get juice out with the garlic press. But with the leaves, I always travel with the plant sap press. So what am I looking at right now? I'm looking at there. Yeah, there's a second
Yep.
presentation right there with the citrus. Yep.
I'm being a little cheeky with the students because a bunch of them have asked for links, and we can't always post links
Oh,
to
okay.
other websites and things.
Yeah.
But they can go to Google and type in your name plus presentations or your name plus bricks or
They all come
whatever,
up.
and YouTube videos and all. It's all out there. The world is
Yeah.
at our fingertips.
Yeah. 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 The first two presentations I've got online now, and the third and the fourth one I do not. But I'm also making new presentations too. So I've got a host of new conferences that are coming up. Some of them have requested new material, others have not, depending upon if I've spoken there before, because they wouldn't want to hear the same thing over and over again. And so there's lots of new material that is being made. So yeah. So right now, just to whet your appetite, I've been whetting your appetite for 2 years about this, but it's the two-spotted spider mite. I've already given a presentation on the aphids. I gave you a little bit of a clue as to what the aphids were doing with the ammonium, but I'm in the process of working on the two-spotted spider mite, and I know that this will be requested relatively soon, probably within the next year. I'd be surprised if I go much longer without it being requested. That's another one, and there are a whole host of other topics that I cover that are sometimes off the beaten path, because I do sometimes deal with odd things like paramagnetism, because my faculty advisor for my PhD was Dr. Phil Callahan. So therefore, I've given presentations on paramagnetism before, and that has to relate to soil. As a matter of fact, that's what I was talking with Elaine with 2 decades ago when I was at the Acres USA conference. We were chatting about paramagnetism and some other things. So, but that's a completely different topic. I've got a number of other topics: biological antenna, various other electromagnetic frequencies and how the plants are involved in them, things of that sort, that I speak out at conferences all the time. So some of the stuff is out there on YouTube and some of the stuff is not. I'm just working as fast as I can before I get too old.
Still have a lot of things to do. And this is a nice motivation for us to keep hunting you in conferences all around the globe.
Okay.
So one more question from Jean. Why can monarch caterpillars eat healthy milkweed plants?
They can't. Thank you, Gene. The milkweed caterpillars are not eating healthy milkweed plants. What they are doing is they are feeding on slightly low brix plants. And the reason why is because a healthy milkweed plant will be too strong for the milkweed, for the monarch butterfly. So because it's too strong, they cannot feed on it. They need a plant that is relatively healthy, but not too unhealthy, but relatively healthy enough that it has the ability to produce the secondary plant metabolites that I discussed that really ramp up at 6. So you're not going to see any caterpillars feeding on milkweed plants below 6 brix. They don't exist. All of the milkweed caterpillars, especially the monarch butterflies and some of the other Danaids that are out there that are attacking the milkweeds, are going after slightly lower brix because they need enough cardiac glycosides in order to become a part of their system. And the cardiac glycosides they take into their system, which confer immunity because they taste bad. So they take the plant secondary metabolites, which usually taste bad. For most insects don't like to eat them. The monarch butterfly is an exception. It is able to contain them and still eat the plant as long as you stay in that very narrow level of making sure the brix is not too high or low. You need enough for the cardiac glycosides to be produced, which means you got to definitely be above 6, but you don't want to be too high because they can get too high and there are some other problems with digestion. So that's why the monarch caterpillar does what it does. This is why the monarch caterpillar is not attacking 14, 15 brix milkweed plants. It is not attacking healthy plants. But that's another one that I get a lot. These are all great questions that are being asked. You are definitely it's like a jigsaw puzzle. All the holes that I left in the presentation are being filled by these questions. So I love that. I really do.
Yeah, our students are awesome in testing our boundaries, which I love them for that because keep us in check. We have to always keep connecting all the dots.
Yeah.
And that's when you know they're really learning, right?
Yes, that's true. That's true.
So one question from Abraham. I love the example bugs provided, but those all seem specialized in some way to focus their attention on and dead or rotten things. What about pests like aphids, potato stem borers, or cotton borers that seem to have their life cycle tied to attacking or invading, if this is an appropriate term, a plant? Wouldn't these creatures have a specialization that leads to injury certain plants? Are there bugs that exist that require attacking a plant in some way to fulfill their life cycles?
Yes, 100% of them. 100% require the plant to be in a particular state in order for it to be eaten. If these plants do not exist, the insect will starve to death and the species will stop growing. You will notice that there are over 1 million species of insects, meaning we have not reached the point where the plants are too healthy for them to consume. But if we go into the jungle where most of the plants are not being consumed or they're being nibbled on, we have to look far and wide in order to find a plant that is being bona fide attacked. And at that point, we know that the brix levels are sufficiently low for that particular plant in order for them to feed upon it. You usually don't find as many aphids in the tropics, but you find them in greenhouses and you find them on a lot of crop plants. But when you go into the tropics, you don't find a lot of aphids. What you do find are a lot of pteridiniids, which are the katydids. A lot of katydids, really cool looking katydids out there. They look like a leaf. They don't look like a leaf. Their legs look like a leaf. They're prized by a lot of people in the tropics and they like to looking at them. And these are some of the insects that you find in the tropics, among others. You'll find a lot of the chewing insects, a lot of caterpillars chewing on leaves, but not a lot. They don't do a very good job of cleaning out the tropics because the tropic is still there. Kauai is still there too. And so because of that, yes, they are specialized. Insects are specialized to eat crappy plants. Their job is to eat crappy plants. And they do their job very well. And they're very selective about it. And they will go through a field looking for that crappy plant. And they will either lay their eggs on it or they will nestle on it and they will take it down. Locusts will attack a crop, take it all the way down, won't touch the farmer's field right next door. Many other insects will attack a plant. You can have 3,000 insects on a particular plant, nothing on the same species right next to it. So we see this all the time. The plant has to be vulnerable in order for it to be attacked. Otherwise, it won't get attacked and the insect will starve to death. Now, as I said, they never starve to death. There's always something out there. And when you have something that's adequate, their numbers increase. And this is why we see exponential growth of insects in some crop plants that are low brix. We do not see exponential growth in crop plants that are coming in at 10 or 11 brix. They'll get eaten, they'll get attacked. A lot of the chewing insects will attack. Won't be that bad, but you're not going to see the exponential growth. So yes, the question is correct. These insects, all of them, 100% of them, are specialized to only eat certain food.
Yep. Thank you so much. Thank you, Tom. Unfortunately, Dr. Adam and I have to leave. We have other commitments. We really appreciate your time, especially this extra time we had with you. In name of the staff, we want to say thank you to everyone that took your time to be here with us. Even with the extended time, a huge majority of you stayed, so thank you so much. And fingers crossed, we're going to have another session with Dr. Tom pretty soon. So keep working. And Tom, thank you so much. Have no words to express how much you learned today.
Happy to help out. Love to teach students. Love it, love it, love it. Okay.
Thanks so much. And
thank
cheers.
you, Carla. And thank you, Adam.
Thank you, everyone.
Okay,
cheers.
Bye-bye.
Bye.
Don't forget to click that like button, subscribe to our channel, and ring the notification bell to stay updated with all our new videos.